We have another Rosen proof by induction. This time we have the sum of the first n even positive integers. Now, this problem 9 does not give us the formula, does not give us a summation that we are to prove. It wants us to first find that. So we're going to create that hypothesis, that sum, and then prove that what we come up with is true. So the way to do this really is to look at patterns, right? The sum of the first n integers, even integers, positive, is going to be 2 plus 4 plus 6 plus 8 plus 10 plus dot, 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 all the way to some integer n, but it's even. So remember, define even as 2 times some integer will always be even. Just for the sake of consistency, we'll say that odd will be 2k plus 1. So think about why that's true. If I take any integer and multiply it by 2, I get an even integer. 2 times 5 is 10. 2 times 7 is 14. And if I add 1 to every even integer, I get an odd integer. So this is how we define odd and even. So that's why I'm writing this as the sum up to 2n. We could also write the summation notation and say this will be the sum as k ranges from 1 to n. These are the same things. They mean the same things. So we have to hypothesize that this equals some closed form and then prove that what we come up with is true. So the way to do this, again, is to look at patterns. If I sum the first term and only the first term, I get 2. If I sum the first 2 terms, I get 6, because 4 plus 2. Let's do this a little more methodically. If I have the summation, I sum the first term, is just 2. The second term is 2 plus 4, which is 6. The first 3 terms is 2 plus 4 plus 6. And that is 12. First 4 terms is 2 plus 4 plus 6 plus 8 is 20. And so on and so on. So this is, if I sum to some n, and n is 1, I get 2, n is 2, I get 6, n is 3, I get 12, n is 4, I get 20, and so on. So we want to conjecture a formula. 2n, this tells us it's even. So let's look at how to maybe write these as factorizations. And we can think of this as prime factorizations. So 2 is 1 times 2. 6 is 2 times 3. Now 12, I could write it as 2 times 2 times 4. But let's write that as 4 times 3, or 3 times 4. And 20, we can think of as 2 times 2 times 5. But let's write that as 4 times 5, and so on. So we can kind of see a pattern here. It's the first term n. I'm taking n. Remember, n is 1, ranging through whatever we terminate. In this case, well, if I think of this more like k, that's probably better, right? If I say it starts at k as 1 and goes all the way to n. So here I'm multiplying k and k plus 1. If k is equal to 1. If k is equal to 2, I'm multiplying k and k plus 1. So a valid hypothesis then would be, well, if I sum from 1 to n of 2k, let's say that we get n times n plus 1. And that's just based on this pattern, 1 times 2, 2 times 3, 3 times 4, 4 times 5. I'm multiplying 1 times 2, and then the next time I'm multiplying 2 times 3, so I'm multiplying consecutive integers. So that's our hypothesis. Let's circle that. This is possibly true, but now we're going to prove it by induction. So the induction proof, this is part B, is we want to show that 2 plus 4 plus 6 plus ... plus 2n is equal to n plus 1. So let's start with the base case. The base case we could think of as the first term. Remember, this is n equals, or n greater than or equal to 1. So here n is 1, or the first term is 2. We could also think of it as being this handy little formula, which is 2 times 1, which is 2. Now, that's the left-hand side. So the left-hand side is 2. And the right-hand side is 2n, or sorry, n times n plus 1, which is 1 times 1 plus 1, which is 1 times 2, which is 2. So indeed, the left-hand side and right-hand side are the same. So the base case holds. So far, so good. So let's do the inductive step. And here we're going to assume that our hypothesis is true. So 2 plus 4 plus 6 plus all the way to 2n is indeed equal to, but I'm going to replace n here with k and say this is true when k is greater than or equal to 1. So that's the induction hypothesis. And sometimes I write IH, so I remember to use it, because anytime that you're doing a proof by induction, you're going to use the induction hypothesis. If you don't, most likely you've made some assumption that you're not supposed to, or something else went wrong in your algebra. Even if you get to the right spot, look to see, maybe you use the induction hypothesis without knowing it, but you're going to use the induction hypothesis always. So what do we want to do now? We want to show that the k plus 1 case is true. Meaning, if I take the left-hand side here and I add another term, so say 2k plus 2k plus 1, I want to show that that's going to be equal to the next case on the right-hand side. So anytime I see a k, I'm going to replace it with a k plus 1. So we have k, so it's k plus 1 times k plus 1 plus 1. Now that right-hand side is ugly, so really it's k plus 1 times k plus 2. So if we can show that the left-hand side and the right-hand side are the same, we've proven by induction that our hypothesis is true. And we found a closed formula for that summation of even integers, even positive integers. All right, so let's look at the left-hand side. In most cases where we have a summation that's equal to some closed form inequality, we're going to make one side look like the other side. And generally, I always pick the summation side, not the closed form side. So the summation side, I'm just going to write, that's the left-hand side. And I want to make this look like the right-hand side. So I'm going to first group it in such a way where I'm going to group the first k terms and then leave the 2k plus 1 guy out here. The reason we're doing that is because what I've highlighted in the parentheses is the induction hypothesis. I made the assumption up here that 2 plus 4 plus 6 all the way up to 2k is equal to k times k plus 1. So I'm going to assume that's true and then use it and say this is equal to k times k plus 1 plus 2k plus 1. So I'm moving this term here. I'm substituting this by the induction hypothesis, by IH. Okay, so let's multiply this stuff out. So we're to distribute k over k plus 1. So take k times k is k squared. K times 1 is k. And let's distribute this guy. So that's 2k plus 2. That is equal to k squared. Now I'm going to group like terms. So k and k. That's 2k plus k gives me 3k plus 2. Not too bad. Now, if I can factor this, it's going to look more like we have over here, hopefully, if we're correct. So remember, factoring a polynomial, a quadratic, is the same as thinking about two binomials, binomials, that if I FOIL, gives me k squared plus 3k plus 2. Well, the trick is what two numbers multiply that give me 2, that when I add them give me 3. It just so happens there's only two numbers that multiply that give me 1, 2 and 1. And if I add 2 and 1, I get 3. So this is indeed equal to k plus 1 times k plus 2, which again is the right-hand side. So our hypothesis that the summation from k equals 1 to n of 2k is equal to n times n plus 1 is true. QED, or I like to put a little box to say proof is over. And that's it. Hopefully that made sense and I didn't do it quickly. So subscribe if you can, or let us know if there's a problem in this Rosen book or any other math book that you want to see, and we will try to upload a video.